Okay, in today's lecture, we're going to cover the first part of the section 5.3 material on double integrals in terms of polar coordinates. And as a motivating example for why we might make use of polar coordinates in this chapter on double integrals, let's consider the following problem. So let's suppose that we want to evaluate the double integral of some function of two variables, f of xy, over a region D, where D is the unit disk x squared plus y squared is less than or equal to 1. So let's visualize our region of integration. Here we're looking at the set of points in the xy plane that lie within the circle of radius 1 centered at the origin. Now this region could be described as a type 1 or type 2 region, making use of rectangular coordinates. We see that the range of x values can go from -1 to +1, and this disk is bounded above by the upper half of our circle, which is given by the function y equals the square root of 1 minus x squared, and it is bounded below by the lower half of our unit circle, which is y equals negative square root of 1 minus x squared. So here the description of our region D in terms of rectangular coordinates is a little bit complicated. If we describe it as a type 1 region, this region D would be the set of all points xy, where x ranges from -1 to +1, and y is bounded above and below by the upper half circle and the lower half circle, plus or minus square root of 1 minus x squared. So if we were to set up the iterated integral to evaluate our double integral of interest, we would have the integral from -1 to 1 with respect to x, and from negative square root of 1 minus x squared to the positive square root of 1 minus x squared of our function f of xy in the order dy dx. And depending on what this function f is, this could get much messier. Now, if we think about describing our region D, that is this unit disk in terms of polar coordinates, we get a much nicer description. So D could be described using polar coordinates as the set of all points with polar coordinates r theta, such that r lies between 0 and 1. So the radius of my circle was 1. So I can move from the center of the circle, that is the origin, outward at most 1 unit. And our value of theta, the angular coordinate, could range from 0 to 2 pi to give us all the points that could lie around this full disk. And we see that that is a much easier description of that region. So let's see how we could integrate a function of two variables over such a region, making use of the polar coordinates r and theta instead of rectangular coordinates x and y. So now that we're talking about polar coordinates, let's give a little review since we haven't seen this in a while. So recall that the polar coordinates r theta of a point in the plane are related to the rectangular coordinates of that same point, xy, by the equations r squared is equal to x squared plus y squared, x is equal to r cosine theta, and y is equal to r sine theta. So let us consider a plane region, let's call it R, which is described by the set of all points whose polar coordinates r theta satisfy that r lies between a and b, and theta lies between two constants alpha and beta. So this sort of region is what is called a polar rectangle. Both coordinates r and theta are bounded above and below by constants. So it's sort of similar to what we saw for double integrals over rectangular regions in the xy plane, but here we would have something called a polar rectangle. So as an example of what a polar rectangle looks like, well, we would have the following figure. So here we have some region R where the radial coordinates for points in this region would lie between r equals a and r equals b, and our angular coordinate theta would lie between the values theta equals alpha, so points along this line formed by rotating alpha units from the positive x-axis in the counterclockwise direction, and we could go up to theta equals beta, which would give us this line segment on the edge of our region formed by rotating from the positive x-axis beta units. So we have this sort of region which we might be interested in integrating over. And let's think about how to convert our double integral of a function f of x and y with respect to area over this region D into an iterated integral making use of polar coordinates r and theta. So the way that we're going to do this is similar to the way that we did it for rectangular regions in rectangular coordinates. We could start by partitioning this polar rectangle R into little subregions. So if I partition my radial interval from A to B into subintervals, I would get these different segments of arcs of a circle where the distance in the radial direction for each of those segments are equally spaced by a factor dr, a small change in the radial direction. Now we could also partition the theta interval from alpha to beta into subintervals, and we would get these line segments through our region that were obtained by looking at lines revolving from the positive x-axis different values of theta between alpha and beta. So these little changes in the value of the theta direction will denote as d theta if we divide it up into little sub-pieces. So now let's think about how to convert our double integral over this region D into an iterated integral. So here we're going to change our x and y values to their values in terms of polar coordinates. So recall that x is given by r times cosine of theta, y is given by r times sine of theta, and we're integrating over our region D, or here we're calling it R for this polar rectangle. And on the end, we have this differential of area, dA. Now, when we were talking about integrating over rectangular regions, dA was just dy dx, or dx dy. It's the little area of one of our sub-rectangles. So now the differential of area in terms of polar coordinates, well, let's think about how we would find it. If we take one of these little subregions, these polar subregions, out of our overall region R, the area of it, which would be a differential of the total area of our region, is given by dr, so that is the length along one of these sides, times the length along this little sub-arc of our circle. Now, the length of the arc of a circle is given by the radius of that circle, that is r, times the angle measure that forms this part of our circle, which we were calling d theta. So here our differential of area is given by r dr d theta. So for our iterated integral, or this double integral in terms of polar coordinates, dA is given by r dr d theta. So this gives us the following result. How to change to the polar coordinate system if we're interested in evaluating a double integral. So let's suppose that we have a function f which is continuous on a polar rectangle r, defined by r ranging from a to b and theta ranging from alpha to beta, where beta minus alpha is between 0 and 2 pi, so we don't go more than a full 2 pi rotation around our region. Then the double integral of our function f of xy over that polar rectangle r is given by the iterated integral, where we take x and y for our function and we replace them by r cosine theta and r sine of theta. And then our differential of area is replaced by r dr d theta. So our inner integral here is with respect to r. So the r values were ranging from a to b for that inner integral, and the outer integral was with respect to theta. So here the outer integral has limits of integration from alpha to beta. So it's important when we are moving to this polar coordinate system not to forget that additional factor of r in the integrand that comes from the fact that the differential of area in terms of polar coordinates is given by r dr d theta. We get that extra factor of r on the end that we want to be sure to remember when we're making this conversion. So now that we have a way to evaluate double integrals over these polar rectangles, let's look at some examples. So in this first one, we are asked to evaluate the double integral of xy over the region D, where we're told that D is the part of the annular region described by x squared plus y squared, lies between 4 and 25, that lies in the first quadrant. So as with our double integrals over general regions, let's start by sketching our region. So here we're looking at just part of some region that lies in the first quadrant. So here we only need to consider the part of our region that lies in this first quadrant. And it's the portion of the annular region x squared plus y squared lies between 4 and 25. So one edge of this region would be defined by the inequality x squared plus y squared equals 4, which would be a circle centered at the origin of radius 2. So here we'd have this segment of our circle lying in the first quadrant, and the other edge of this region is described by the inequality or the equation x squared plus y squared is equal to 25, which would give us a circle centered at the origin of radius 5. So if we look at the portion of that annulus that lies in the first quadrant, we would have this little section of our annulus, or our ring, that lies within that first quadrant. So let's think about how we could describe this region. We see, based on the way it looks, is bounded by circles. It probably wouldn't be very easy to describe in terms of rectangular coordinates, but if we make use of polar coordinates, it's much easier to describe. So here in polar coordinates, our region D could be described by the set of all points r theta such that the radial coordinate r can range from 2 to 5, and our angular coordinate theta we see could range from 0 up until pi over 2, since we're only working in the first quadrant. So here this range of radial values from 2 to 5 means we can consider points where we're moving any distance from 2 to 5 units from the origin, and this range of values for the angular coordinate theta means that we could range from points on the x-axis where theta is 0, or rotating from the positive x-axis by pi over 2 radians, which would give us points along this positive y-axis. So here this region is a polar rectangle. So to evaluate our double integral over this region D of xy dA, we would have the integral where theta ranges from 0 to pi over 2, and the integral where r ranges from 2 to 5. And here x, in terms of polar coordinates, is given by r cosine theta times y, which in polar coordinates is r sine of theta, times the differential of area, which in polar coordinates is r dr d theta. So what we can do here is group some terms within our integrand to simplify. So we have the integral from 0 to pi over 2 and from 2 to 5 of, if we group the r terms, we have r times r times r, or r cubed, and then we're left with a sine of theta times cosine of theta times dr d theta. So one thing that we can make use of here, we haven't seen this much in our work for rectangular coordinates, but recall here that if we're evaluating an iterated integral, we're using the concept of partial integration. We're going to treat one of our variables as a constant and integrate with respect to the other one. So something that will come up a lot, or that will be very useful throughout the remainder of this chapter, is the fact that we can pull constants out in front of integrals. So here, one thing that I might make use of is the fact that my inner integral is with respect to r. Now, if I'm integrating with respect to r, the remainder of this expression, that is sine theta times cosine of theta d theta, is a constant. Now I can pull those constant terms out in front of my integral with respect to r, and I see that even after I evaluate my inner integral with respect to r, the r values for the limits of integration are constants. They don't depend on theta at all. So after I integrate with respect to r, I'm going to have a constant function times these functions of theta. So if I were to pull these theta expressions outside of the inner integral, I would have the integral from 0 to pi over 2 of sine theta times cosine of theta d theta, and then my inner integral is from 2 to 5 of r cubed dr. So here we just have a product of two different integrals, one with respect to r, one with respect to theta. So let's evaluate this first integral. Here, to integrate sine theta times cosine theta, we could make use of a substitution where u is given by sine of theta, so that du is cosine of theta d theta. So here our first integral, if we rewrite in terms of u, would be the integral of u times du. And if we change our limits of integration to u values, well, when theta is equal to 0, u is sine of 0, or 0. And when theta is equal to pi over 2, u is sine of pi over 2, or 1. And then we still have our second integral from 2 to 5 of r cubed dr. So now we have, for the antiderivative of this first function, 1/2 u squared being evaluated from 0 to 1. And then we're multiplying by 1/4 r to the 4th, evaluated from 2 to 5. So this first value gives us a 1/2 minus 0. And when we substitute into this, or the value of the second integral, when we substitute 5, we have 5 to the 4th, or 25 squared, which is 625 divided by our 4. Minus, when we plug in 2 for r, we have 2 to the 4th, or 16 divided by 4, leaves us with a value of 4. So after we simplify our terms, we're left with 609 over 8 for the value of that double integral over the indicated region. So we see in this first example that for certain regions, they are much more easily described in terms of polar coordinates instead of in terms of those rectangular coordinates x and y. So let's look at some other examples. In this next one, we are asked to find the volume of the solid bounded by the paraboloid z equals 16 minus 3x squared minus 3y squared, and the plane z equals 4. So let's try to visualize this solid region that we're describing. Our first equation here is the equation of the paraboloid, 16 minus 3x squared minus 3y squared. So that is a circular paraboloid, which is opening downward and has its vertex at the point 0, 0, 16 in space. And then it is being bounded below by the plane z equals 4. So we have some plane 4 units above the xy plane, and that plane is going to intersect our paraboloid in a circle. So here we will have a solid that lies between those two surfaces, below this paraboloid and above that plane z equals 4. So in order to find the volume of a region or of a solid bounded by two surfaces, we could find the area or the volume that lies underneath our first surface, and then find the volume that lies underneath the lower surface, and take the difference of those two values to get the volume between these surfaces. Now, in order to evaluate the volume underneath the surface, we need to know what region we're integrating over. So here, to determine that region, let's see what curve defines the intersection of these two surfaces. Now, to find the equation for the curve of intersection, we're going to set our surfaces equal to each other. So here, if we let 4 equal to 16 minus 3x squared minus 3y squared, then we would have, if we move all of our variables to the left-hand side, 3x squared plus 3y squared is equal to 12, moving all our constants to the right. And then dividing through by 3, we have x squared plus y squared is equal to 4. So this circle of intersection for those two curves is a circle of radius 2, centered around the z-axis. The center of the circle would be x equals 0 and y equals 0. So if we think about projecting this solid region onto the xy plane, we have a circle for the outline of our region, described by x squared plus y squared is equal to 4. And we're going to integrate over the region that lies inside of that circle. So here our region of integration D would be the disk defined by x squared plus y squared is less than or equal to 4. So this plane, z equals 4, lies 4 units above the xy plane, and our upper value or upper boundary for this solid region is our parabola, 16 minus 3x squared minus 3y squared. So to find the volume of the solid region bounded by these two surfaces, let's call that volume V, we would be evaluating the double integral over our region D of the upper surface. So here 16 minus 3x squared minus 3y squared. So geometrically what we have so far would give us the volume of the solid that lies above that disk D and below our surface, so this full solid shown here in red. And then to get the volume of the solid bounded by these surfaces, we would then have to subtract the volume of the surface that lies above our disk D and below this plane Z equals 4. And to get that volume, we would integrate the double integral over D, the constant function Z equals 4. So here, integrating with respect to area. So we find, after some simplification, the double integral over D of 12 minus 3x squared minus 3y squared, dA. So now here, to evaluate this double integral over the disk D, we need to set it up as an iterated integral, and the disk D that we're talking about here can be described in terms of polar coordinates as the set of points r theta such that r ranges from 0 to 2. This is a circle of radius 2 in the xy plane. And our theta value can range from 0 to 2 pi. Since we're talking about everything inside of the full circle to get our disk. So in terms of polar coordinates, we would have the integral from 0 to 2 pi and the integral from 0 to 2 with respect to r. And changing our function to polar coordinates, we have 12 minus, if I factor out a 3 from my, or a negative 3 from my x squared and y squared terms, I've got a negative 3 times x squared plus y squared, which is r squared. And the differential of area, dA, is given by r dr d theta. So here, if we collect some like terms, we have the integral from 0 to 2 pi and 0 to 2 of 12r minus 3r cubed when we distribute our r times dr d theta. So again, in this example, I can make use of the fact that this inner integral with respect to r, after we evaluate this integral with respect to r and plug in the constant values of r for our limits of integration, we will just have a constant. So I could pull this entire constant out in front of my integral with respect to theta, and I would have the integral from 0 to 2 of 12r minus 3r cubed dr times the integral from 0 to 2 pi of d theta. Now this second value, we're integrating a constant 1 over the interval from 0 to 2 pi, which would give us just the length of our interval, 2 pi. So here we have a constant 2 pi times the integral from 0 to 2 of 12r minus 3r cubed dr. So again, making use of the fact that that inner function works out to be a constant with respect to theta, we see that for our outer integral, we would just be left with this factor of 2 pi times our inner integral. So let's evaluate that inner part now. We have our constant 2 pi times the antiderivative of this function would be 6r squared minus 3/4 r to the 4th, evaluated from 0 to 2. So this leaves us with 2 pi times, if we evaluate at r equals 2, we have 24 minus 16 times 3/4 would be 12, and then we subtract what we get when we plug in 0 for r, which is 0. So we're left with 2 pi times 12, or 24 pi cubic units for the volume of this solid of interest. All right, so let's look at a similar problem to what we've been considering, but where our region of integration may not be a polar rectangle necessarily. So we can generalize the discussion that we were having for polar rectangles to double integrals over polar regions, which may not have constant values for theta or r. So here let's suppose that f is a continuous function on a polar region D, described as the set of all points r theta, where theta lies between two constants alpha and beta, but where r is no longer bounded by constants, but functions of theta, let's say h1 and h2 of theta. So the region that we would be describing here might look something like the following. So let's say in the plane, we lie between two constant values of theta. Let's say the line defined by theta equals alpha, and the one defined by theta equals to beta. But our radial coordinates, let's say, are bounded by functions of theta. So maybe not just circular arcs, but we might have some curve of varying radius, where the outer curve would be described or be the graph of h2 of theta, and that inner curve by h1 of theta. So our r values would lie, or the points r theta would lie within this shaded region. So this would be a description of our region D. And to evaluate the double integral of a function over that region, we could set this up as an iterated integral of the function f of xy, where x and y are replaced by r cosine theta, r sine theta, where the inner integral with respect to r can range from the function h1 of theta to h2 of theta, and the outer integral with respect to theta would range between the constants alpha and beta, and where our differential of area is again given by r dr d theta. So let's consider an example of a double integral over a region bounded by a function or a polar curve, which would be the graph of a function of theta. So in this next example, we're asked to evaluate the double integral over the region D of square root of x squared plus y squared, where D is the region bounded by the cardioid 1 plus cosine of theta. So recall that a cardioid is sort of a heart-shaped curve. In this particular cardioid, 1 plus cosine of theta is describing a curve that looks like the following. So here, our region of interest D would be this shaded region. And we see that it's described by this polar curve r equals 1 plus cosine of theta for this radial coordinate. And to trace out the full cardioid, our range of theta values would have to be from 0 to 2 pi. So to trace out this full edge through all 4 quadrants. So here, let's start by describing the region D in terms of polar coordinates. It'd be the set of all points r theta such that theta is ranging from 0 to 2 pi, and r would range from 0, since the origin is considered within our region, and the outer edge of this region is given by the cardioid, 1 plus cosine of theta. So, in order to evaluate this double integral of the square root of x squared plus y squared over d, let's express this as an iterated integral. So our outer integral with respect to theta would range from 0 to 2 pi, and the inner value would range from 0 to 1 plus cosine of theta. Now the function that we're integrating was the square root of x squared plus y squared. Now x squared plus y squared is equal to r squared in terms of polar coordinates. So taking the square root of that value, we have r. And then we're multiplying by the differential of area, which is r dr d theta. So combining some like terms, we have the integral from 0 to 2 pi, integral from 0 to 1 plus cosine of theta of r squared dr d theta. Now, in this example, we might be tempted to use the same sort of shortcut or trick that we did in the previous examples, where we would think about our inner function or our inner integral with respect to r as being constant with respect to theta. However, we can't do that in this case, because when we evaluate this inner integral with respect to r, when we plug in that upper limit of integration, 1 plus cosine of theta, we see it depends on theta. It is no longer a constant with respect to theta, so I can't pull it out in front of that d theta integral. Here I have to evaluate from the inside out. So let's start by finding our antiderivative of the function with respect to r. So this gives us the integral from 0 to 2 pi of 1/3 r cubed, evaluated from r equals 0 to 1 plus cosine of theta d theta. So we substitute the value of 1 plus cosine of theta in place of r. So we have here a 1/3 1 plus cosine of theta quantity cubed, minus when we plug in 0 for r, we have 0. So we then integrate with respect to theta. Now to evaluate this integral, we need to expand 1 plus cosine of theta quantity cubed, and then distribute our 1/3. So here, when you expand and distribute that factor of 1/3, you are left with 1/3 plus cosine of theta plus cosine squared theta plus 1/3 cosine cubed theta, d theta. So to find our antiderivative, we could look at each term individually. And the antiderivative for the first two terms isn't so bad. We have a 1/3 theta, or theta over 3, plus sine of theta. And those first two terms we're evaluating from 0 to 2 pi. And then we are adding the integral from 0 to 2 pi of cosine squared theta. Now recall, to evaluate the antiderivative of cosine squared, we would have to make use of the trig identity, where cosine squared is equal to 1 plus cosine of 2 theta all over 2, integrating with respect to theta. And then for our last term, we have the integral from 0 to 2 pi of cosine cubed. Now to integrate an odd power of cosine, we could peel off one factor of cosine. So here, if I pull my constant 1/3 out in front and factor out one power of cosine, I have cosine squared theta times cosine theta d theta. And let's see what we would get for the antiderivatives of those last two pieces. So this first term, if we evaluate at 0 and 2 pi, gives us 2 pi over 3 plus sine of 2 pi, which is 0. And then subtracting what we get when we plug in 0, we have 0. So just a 2 pi over 3 for that first term. Then we are adding, for this second piece, our antiderivative of 1/2 would be theta over 2. And the antiderivative of cosine of 2 theta over 2 gives us a 1/4 sine of 2 theta, which we're evaluating from 0 to 2 pi here. Now for this last part, we have a constant 1/3 out in front. And to integrate cosine squared theta times cosine of theta, we rewrite cosine squared as 1 minus sine squared of theta. And we have a cosine of theta d theta. And then we're going to make use of a substitution. U equals sine of theta, so that du is equal to cosine theta times d theta. So let's evaluate each of these pieces. From our first integral, we had a 2 pi over 3, plus evaluating this second antiderivative at 2 pi, we would have pi plus 1/4 times sine of 4 pi, which is 0. And then we subtract what we get when we plug in 0 for theta, which is 0. Now for this last term, if we rewrite our integral in terms of u, we would have the integral of 1 minus u squared du. And then let's change our theta values to u values. Now if theta is equal to 0 or 2 pi, u, which is sine of theta, would be 0 for both our upper and lower limits. So recall, if you're integrating over an interval of 0 length, that is from 0 to 0, the value of this integral is 0. So we're left here with just 2 pi over 3 plus pi, which leaves us 5 pi over 3 total. So here we end up with an integral involving several different powers of cosine, which gets a little tedious because we have to use different techniques to handle that cosine squared or cosine cubed term. But if we recall our techniques of integration from Cal 2, it's not terribly messy here. So let's look at another one. In this next example, we have the double integral of x over the region D, where D, we're told, is the region in the first quadrant, which lies between the circles x squared plus y squared equals 4, or in terms of polar coordinates, r equals 2, the circle of radius 2, and the circle x squared plus y squared equals 2x, or rewriting this in terms of polar coordinates, x squared plus y squared is r squared. That's equal to 2 times x, which is r cosine theta. So dividing both sides by r, we have r equals 2 cosine of theta. So let's think about visualizing our region of integration and then see how we could describe it in terms of these polar coordinates. So here we're looking at the part of the region bounded by these two circles in the first quadrant. So we only need to consider the first quadrant of the xy plane. And our first circle was x squared plus y squared equals 4, or r equals 2. So that is the circle centered at the origin of radius 2. And the other circle, which forms the edge of our region, was x squared plus y squared is equal to 2x, or r equals 2 cosine theta. So tracing out this circle using polar coordinates, we have a circle of radius 1 centered at the point 1, 0. So here, the region in the first quadrant bounded by those two polar curves or circles would be given by this shaded region. So in terms of polar coordinates, let's think about how we could describe that region. We could think about it as the set of all points whose polar coordinates are theta, are bounded by theta equals 0 or pi over 2, since we're only working in the first quadrant. And then our radial coordinate is bounded by these two functions of theta. The inner edge of our region D is this 2 cosine of theta circle, and the outer edge is the circle of constant radius 2. So to set up our iterated integral for this double integral of x over the region D, we would integrate with respect to theta from 0 to pi over 2, and with respect to r from 2 cosine of theta to 2. And the function we're integrating is x, which in terms of polar coordinates is r cosine theta, and the differential of area is given by r dr d theta in terms of polar coordinates. So here we have the integral from 0 to pi over 2, and from 2 cosine theta to 2. Combining our factors of r, we have r squared cosine of theta dr d theta. Now again, in this example, we can't make use of the shortcut or the trick where we pull out our inner integral with respect to r in front of the theta integral. And the reason is when we evaluate with respect to r, and we plug in this lower limit of integration, we have a function of theta. It is not constant with respect to theta. So we have to proceed from the inside out. So if we integrate first with respect to r, we have a 1/3 r cubed times cosine of theta, evaluated from 2 cosine theta to 2, and then integrate with respect to theta. So let's see what we have here. This is the integral from 0 to pi over 2. When we evaluate at r equals 2, we have 8/3 cosine of theta, minus when we evaluate at 2 cosine of theta, we will have 8/3 cosine theta to the 4th power, and then integrating with respect to theta. So here we can factor out an 8/3 from each term, and let's see what we have. Evaluating the first antiderivative, or the antiderivative of the first term, we have 8/3 times sine of theta, evaluated from 0 to pi over 2. So this leaves us with 8/3. And then we are subtracting our constant 8/3 we can pull out in front of the integral from 0 to pi over 2. And to evaluate cosine of theta to the 4th power, well, we can think about it as cosine of theta, or cosine squared of theta squared. Now we saw in the last example, cosine squared theta is given by 1 plus cosine of 2 theta all over 2. Now since we have cosine to the 4th, well, that's the same as cosine squared. So we have to write each factor in terms of 1 plus cosine of 2 theta over 2. So let's see what we have here. We can pull out the constant factors, 1/2 times 1/2, or 1/4, out in front of our integral. And since we already had the constant 8/3, we're left with 8 over 12, or 2/3, of the integral from 0 to pi over 2. And we are left with a 1 plus cosine of 2 theta times 1 plus cosine of 2 theta. So if we expand, we would have 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta, d theta. So we have 8/3 minus 2/3 of the antiderivative of our first term is theta. The antiderivative of this next term would give us a plus sine of 2 theta. And here we're evaluating those first two terms from 0 to pi over 2. And then our last term, we had a constant of negative 2/3 out in front. We were left with the integral from 0 to pi over 2. And now this cosine squared of 2 theta, well, again, to integrate an even power of cosine, we make use of this same trig identity. So we have 1 plus cosine of twice the angle 2 theta would give us a 4 theta all over 2, and then integrating with respect to theta. So let's see what we're left with here. We had an 8/3 minus 2/3 times, evaluating this antiderivative at pi over 2, we have pi over 2 plus sine of pi, which is 0, And then evaluating at theta equals 0, we are subtracting 0. So now, for this last term, we have a negative 2/3, and the antiderivative of 1/2 would be theta over 2, plus the antiderivative of cosine of 4 theta over 2 gives us a 1/8 sine of 4 theta, which we are evaluating from 0 to pi over 2. So we have an 8/3 minus our 2/3 times pi over 2 leaves us with pi over 3. And then evaluating this last term, we have our negative 2/3 out in front. Plugging in pi over 2, we have pi over 4, plus 1/8 times sine of 2 pi, which would give us 0, minus when we plug in 0 for theta, we have 0. So we're left with 8/3 minus pi over 3, minus, for this last term, we get 2 pi over 12, or pi over 6, and this simplifies to 8/3 minus, let's see, 4 pi over 6, or 2 pi over 3 for our final answer here. So we see that in this case that the region is bounded by polar curves. We sometimes get these messy expressions involving powers of sine or cosine, and we have to think back to our Cal 2 techniques to see how to integrate those functions.